Have you ever wondered what makes up everything around us? From the air we breathe to the stars in the sky, everything is made of tiny particles called atoms. These minuscule building blocks are the heart of matter, and understanding them unlocks a universe of knowledge. Join us on a captivating journey as we delve into the atom's core, exploring its structure, the enigmatic subatomic particles, and the groundbreaking discoveries that have shaped our understanding of the universe. For centuries, philosophers and scientists pondered the nature of matter, proposing the existence of indivisible particles called atoms. However, it wasn't until the late 19th century that experimental evidence began to illuminate the atom's secrets. This marked the beginning of a scientific revolution, revealing the astonishing complexity hidden within these fundamental units of matter. Our exploration begins with the pioneers who dared to probe the atom's depths, uncovering the subatomic particles that make up its structure. From the negatively charged electrons to the positively charged protons and the elusive neutrons, each discovery brought us closer to comprehending the atom's intricate design. Prepare to be amazed as we unravel the mysteries of the atom, revealing the elegance and order that govern the universe at its most fundamental level. Fasten your seatbelts as we embark on this exhilarating journey into the quantum realm, where the laws of classical physics give way to the perplexing yet fascinating world of quantum mechanics. Get ready to explore the profound implications of atomic structure, from the development of modern technologies to our understanding of the universe's origins. In the late 19th century, a curious phenomenon known as cathode rays captivated the scientific community. These rays, emitted from a negatively charged electrode or cathode in a vacuum tube, held the key to unlocking the atom's secrets. It was J.J. Thomson, a brilliant British physicist, who would rise to the challenge, conducting a series of ingenious experiments that would forever change our understanding of the atom. Thomson's experiments involved passing cathode rays through electric and magnetic fields. By carefully observing the rays' deflection, he made a groundbreaking discovery. Cathode rays were not rays at all, but streams of negatively charged particles, much smaller than atoms. He called these particles corpuscles, but they would later become known as electrons. This revelation shattered the prevailing notion of atoms as indivisible spheres, paving the way for a new era of atomic theory. Thomson's discovery of the electron, the first subatomic particle ever identified, earned him the Nobel Prize in Physics in 1906 and cemented his legacy as one of the fathers of modern physics. His work laid the foundation for further exploration into the atom's structure, igniting a scientific revolution that continues to this day. While Thomson's discovery of the electron shed light on the negatively charged constituents of atoms, it raised a perplexing question. If atoms are electrically neutral, there must be a positive charge counterbalancing the negative charge of electrons. Enter Eugen Goldstein, a German physicist, who would make a crucial contribution to our understanding of the atom's structure by identifying the elusive positive particle. Goldstein's experiments, conducted in the late 1880s, involved modifying the cathode ray tube by using a perforated cathode. He observed that while cathode rays streamed towards the anode, another type of ray, composed of positively charged particles, moved in the opposite direction, passing through the holes in the cathode. He called these rays canal rays. By analyzing the deflection of canal rays in electric and magnetic fields, Goldstein determined that they were much heavier than electrons and carried a positive charge. This discovery provided crucial evidence for the existence of a positively charged counterpart to the electron, later named the proton by Ernest Rutherford. Goldstein's pioneering work, though often overshadowed by Thomson's electron discovery, played a pivotal role in shaping our understanding of the atom's internal structure. Section 4. Cracking the atomic nucleus, Chadwick's neutron discovery. The discovery of the electron and proton marked significant milestones in unraveling the atom's structure. However, a crucial piece of the puzzle remained elusive. Physicists knew that protons and electrons alone could not account for the total mass of atoms, suggesting the presence of another, yet undiscovered particle within the atom's core. In 1932, James Chadwick, a British physicist, made a groundbreaking discovery that would complete our understanding of the atom's basic building blocks. Chadwick was studying the effects of bombarding beryllium atoms with alpha particles, which are helium nuclei. He observed the emission of a highly penetrating radiation, initially thought to be gamma rays. However, Chadwick's meticulous experiments revealed that this mysterious radiation behaved differently from gamma rays. It interacted weakly with matter, indicating a neutral charge, and had a mass similar to the proton. He concluded that this radiation consisted of neutral particles, which he named neutrons. The discovery of the neutron revolutionized our understanding of the atom. It explained the discrepancy in atomic mass, providing the missing piece of the atomic puzzle. Chadwick's groundbreaking finding earned him the Nobel Prize in Physics in 1935 and paved the way for further advancements in nuclear physics, including the development of nuclear energy and the understanding of nuclear reactions in stars. Section 5. Early atomic models, from plum pudding to a miniature solar system. The discovery of the electron, proton and neutron in the late 19th and early 20th centuries provided the building blocks for understanding the atom's structure. However, the question of how these particles were arranged within the atom remained a mystery, prompting scientists to propose various atomic models. J.J. Thomson, the discoverer of the electron, proposed the plum pudding model in 1904. This model envisioned the atom as a positively charged sphere with negatively charged electrons embedded in it, much like plums scattered throughout a pudding. This model, though a significant step forward, was short-lived, soon to be replaced by a more accurate representation of the atom's internal structure. In 1911, Ernest Rutherford, a New Zealand-born physicist, conducted his now famous gold foil experiment, which would revolutionize our understanding of the atom. Rutherford and his team bombarded a thin gold foil with alpha particles, expecting most particles to pass through with minor deflections, as predicted by the plum pudding model. To their astonishment, a small fraction of alpha particles were deflected at large angles, with some even bouncing back towards the source. Rutherford interpreted these unexpected results as evidence for a small, dense, positively charged nucleus at the atom's center. He proposed a new atomic model, the nuclear model, in which electrons orbited the nucleus much like planets orbiting the sun. This model, a significant departure from Thomson's plum pudding model, marked a turning point in our understanding of the atom and established the basic framework for all subsequent atomic models.